Hi everyone, and welcome to this lesson on deductive reasoning. This is sort of an introduction to mathematics as a whole. So mathematicians are always writing arguments, or what they call proofs, using deductive reasoning, which is just the act of drawing conclusions from a set of premises. So let's look at an example. A simple argument is all cats are animals, Fluffers is a cat, and therefore Fluffers is an animal. So in this simple argument, the first two statements are the premises. So these are our premises, and the last statement is the conclusion. That is, the first two statements are assumptions. All cats are animals, and that Fluffers is a cat. There are two ways that the argument could fall apart, and one is that these premises may not be true. So what if Fluffers isn't really a cat? Maybe that's what I call my motorcycle. Then this whole logic would be invalid, because Fluffers isn't actually a cat. But we're going to take as true that Fluffers is a cat, and that all cats are animals. In math, we don't usually argue about the truth of premises, and we just assume that those statements are true. The statements that we assume are true are called axioms. So an axiom is a statement that is assumed to be true. In our arguments in mathematics, we don't only begin with axioms, although the foundation of mathematics is axioms. So when we derive statements, for example, that Fluffers is an animal, we might use that as a premise for another argument. So premises may be axioms, or they may be derived statements. But what we are concerned with in math more often is making valid deductive arguments. So given a set of axioms, we want to know whether a conclusion is actually true, and this is based on logic. So this is our introduction into the topic of logic. When we're dealing with logic, we're going to deal with statements, which are sentences that are either true or false. So here's a few examples of statements. I went to the store today. That is either true or false, because either I did go to the store or I did not. Green is the best color. Could be thought of as a statement, because you either think, yes, green is the best color, or no, it isn't, at least at this given time. And a statement could be a mathematical statement, such as an odd number times an odd number is an odd number. Well, that is always true, so this is in fact a statement. Not every sentence is a statement, though. For example, wow. Well, that's not a statement. It's not true or false. It's just an exclamation. Obviously, a question is not a statement. Where were you today? It's not a true or false. And sometimes instructions, such as the door on the left, isn't a statement. The door on the left is, well, in fact, just a part of a sentence. So what we are concerned with are statements. Things we can say, yes, this is either true or false. And of course, the third statement is most likely the kind of thing we would look at in mathematics. So when making arguments, of course, we make arguments with language. And language is an imprecise tool. So mathematicians actually give extra definition to language, or their own definitions to language, if you'd like to say that. And with these mathematical conventions, we can be a little bit more accurate about what we're saying when we make an argument. And as you'll see below, we often use letters such as P or Q to represent a statement. So whenever you see P or Q below, that means something that's either true or false. The first thing that we're going to use is negation, which is to say not P. If P is a statement, the negation of P is not P. However, whenever we write this in English, it's not going to sound like not P. So a statement P could be, I went to the store today. This, in this example, is P. And the negation is, I did not go to the store today. So this is not P. So I didn't say not I went to the store today. In other words, we don't actually say not P, but logic would say we have the statement P and the negation is not P. In English, we're going to have to convert that into something that negates the statement in meaning. So to say I went to the store today, to negate that, the meaning is I did not go to the store today. A conjunction is just an and statement. So for example, if we say bears are not strong and bears are not very smart. So this is like P is bears are not strong, Q is bears are not smart. Then we could say bears are not strong and bears are not smart. That's a conjunction of the two statements. But in English, we say this in all sorts of different ways, right? So that's number one, which would be pretty much a literal conjunction of those two statements. But we can make it a little more concise by saying bears are strong and not very smart. So that's just a little bit of concision, but logically, it's the exact same thing. And the word but also acts as a conjunction. So a third way to say this is bears are strong, but not very smart. Logically, it's all equivalent. So all of these are conjunction, and in logic, we always use and to represent this. We won't use P but Q. So you have to be pretty careful when converting from mathematics to English and back. You can make the English sound completely different than what the logic sounds like. And trying to convert from English to logic is what you need to do whenever you're understanding a mathematical proof. What is logically being said here in this proof, even if the English doesn't sound like logic. The next one is a disjunction, which is to say or. So here P or two statements P and Q. The disjunction of those two is P or Q. However, and this is pretty interesting because a lot of people don't realize this, there are actually two uses of the word or in English. One is the inclusive or, which means one or the other, or both. The other is the exclusive or, which means one or the other, but not both. So let's look at examples. An example of the inclusive or would be, if you are a parent or teacher, you should encourage your kids to learn programming. So, of course, if you're a parent only and not a teacher, that means to encourage your kids. If you're a teacher only and not a parent, you should encourage your kids. But if you're both a parent and a teacher, then of course you should still encourage your kids to learn programming. So that's an inclusive or, meaning one or the other or both. An exclusive or that we often use in day-to-day language would be something like, can we get pizza or lasagna for dinner? And this, it implies pizza is okay for dinner and lasagna is okay for dinner, but you don't really mean that you want both pizza and lasagna for dinner. So you should get one or the other, but not both. So, as I said, this can get a little bit complicated. For example, if we say neither P nor Q, what we mean, logically, is not P and not Q. So why do we need both these English statements and this logical breakdown? Well, mathematicians write arguments in English statements because we're not robots, right? It's easier to understand English from a human perspective. And writing everything in pure logic and trying to discuss things in pure logic is just completely unnatural for humans. However, we want to accurately parse what these arguments are saying. So we can take the English statements and, in our minds at least, scramble them up and parse them into logical statements. That way we can break down arguments. And we look for holes in the arguments by looking at the logic, especially in mathematics. So if you were in law or something else, you could attack both premises and the logic. In mathematics, we just make these assumptions or axioms. So usually that's not what we're looking at. If you have bad assumptions, then the argument doesn't even get off the ground. And in the future lessons, we're going to talk about how to make good arguments based on logic. All right, so I'll see you all in the next lesson.